Right. Today we're going to look at a new subject in the field of controls, that is Lyapunov stability. Uh, you have studied stability criteria in early semesters, right? This is a new one, right? And it's a different approach altogether. The technique was proposed by this gentleman, Lyapunov, and there were many Russian-based mathematicians who developed algorithms for controls, right? Different theorems and all, but they are not very regularly reported in the Western world because of the language and exposure. What we know as controls is what the Western world publish in English, right? But there are a lot more in the field of controls coming from Russia and Europe, right? Non-English. So let's look at what we have here. So if you look at the stability definition, you can see this terrain here, right? There's a uphill here and also a trough here, right? And if you put a little small object which is rolling spherical kind of thing, right? And depending on the position, right, they tend to move or stay stable. Say, for example, if you select point A and if you put the object there, and if you deflect it a little bit, we call it perturbation. Okay, if you perturb the object at point A, it will fall, right, to the left or to the right immediately, right? And if you select your point as you can see it over here, C, right? If you perturb it left or right, it will always come back to the stable point, right? This is exactly opposite of what you would experience when you place the object over here. And yet another scenario, if you place the object somewhere around B, which is a flat, perfectly flat plane, the object will stay there wherever you place it. And even if you deflect it or perturb it to left or right, it will move to another point and stop. Okay, so everywhere it is stable, right? It doesn't come back to the original point or doesn't start keep moving indefinitely, right? So these are a state of motion of an object depending on where it is. So if you look at the mathematical description of stability, a system is stable if the output is bounded for all bounded inputs. So this is a different way of defining stability, right? When you give an input to the system change. So when I say system change, I really refer to the state variables, right? There are state variables in the plant. If a second order system, it has 2 states, third order has 3 states, like that. These states change: position, velocity, acceleration. These are the kind of states in a moving plant, okay? If you give a bounded input, which means limited input, right? Like your control signal, which has a limit, negative and positive, right? It's not unbounded. You can't have infinite force, infinite energy to the plant, right? Always it is finite. So then for finite input, you get finite output. Okay, that is what it says. So then the system is stable. So when the output is bounded, which means it doesn't go up or down indefinitely. Okay, it goes to a certain level and stay there. That is what is called stability. Okay, it doesn't mean it doesn't move at all, right? Even if the state changes, if it finds another stable point somewhere, right, and stay there, system is stable. So the stability is a property of a system. So once you have the model of the system, right? The stability is already embedded in the system. Say, for example, um, if you recall any of the plants you dealt with in the first semester, or some plants you dealt this semester in state space model, yeah, you saw the system matrix, capital A, remember? So capital A has the stability information within it. If you carefully analyze matrix A, system matrix, you can forget about other things. You can deduce from A whether the system is stable or not. So again, if the system is stable, the state variables will not go to infinity, negative or positive, right? For bounded input. So unstable systems are not like that. Unstable systems, even if you give a bounded input, right, output changes to infinity gradually. System is unstable. So system gets more and more energy, and it drives the state variables without stopping, right, to infinity. So at some point of time, system breaks. So systems have equilibrium states, right? The equilibrium states can be unstable, like for example here, this is an equilibrium state, but it's very fragile. The moment you perturb it, it will fall right to the left or to the right. And also an equilibrium point can be neutral. Some here it's a neutral equilibrium, right? Because it can actually change the equilibrium point to another point and stay stable there, right? Or it could be unstable equilibrium, right? Over here, right? It is very fragile. So this one over here is the stable equilibrium, right? Which is actually the point object is coming back to original point, even if you deflect it. So unstable equilibrium, stable equilibrium, and neutral equilibrium, right? Okay. Now, if you summarize things you have done relevant to stability of a plant, right? You can see some of these things. There's a very simple test for system stability, right? All what you need to find out is find out the poles of the plant, okay? You remember characteristic equation, this one, Si minus A determinant equals to 0. So once you know the system matrix, put it in here, Si minus A, get the determinant, set it to 0, solve for eigenvalues. So the values you get from here are the eigenvalues of matrix A. Remember that, okay? You find the eigenvalues of system matrix A. Or we call it closed loop poles of the plant, right? Then you check the real part of the solutions, eigenvalues, or the poles, right? If they are here like that, right, you will see a negative real part. Then we say the system is stable. Okay, we studied these things. And if the eigenvalues or the poles of the plant have positive real parts, the system is unstable. Okay. And if the poles have 0 real parts, then system is marginally stable. Oscillatory, but oscillations do not grow, and they neither decay over time. They maintain the same amplitude. So system is marginally stable. Why we say that? If you look at the time domain response for a step input, you give a step signal to the plant, and when you solve the equations, you get this type of response: C e to the minus rho sigma tau cos omega t plus psi. Okay, so this is the real part of the eigenvalues, right? Or the closed loop poles. So if the sigma is this one, sigma is positive, but with the negative one, the whole part is negative. Okay, this minus sigma is over here. So then what you get is decaying sinusoidal, right? It's cosine waveform, but in front of that you have this amplitude, which is getting smaller and smaller and smaller as time goes on. Okay, so that is why we say negative real parts tell us that the response gradually decay down to zero with time. So that system is stable. On the other hand, if this minus sigma, right, is on the right hand side, is positive, then this is growing. The amplitude of the cosine increases, so which means growing sinusoidal, and system is unstable. Right. So this is just a little recap of what we have done. If we summarize, if sigma is less than zero, unstable, right? Which means minus sigma is positive. Minus sigma is the real part of the poles. So if it is zero, margin stable. If it is greater than zero, unstable. Okay, right. Then you have the other technique, Routh-Hurwitz criterion. There, it determines stability based on transfer function coefficients, right? When you have the transfer function, you have the denominator, numerator transfer function. Look at the denominator transfer function, right? Which is what we call characteristic equation when you set it to zero. But here we are not going to solve this characteristic equation equals to zero equation, but we look at the coefficients and put it in an array, and there's a little process, right? And then you figure out whether the system is stable or not. We don't know actual poles of the plant or the eigenvalues, we don't know, but we can clearly say whether the plant is stable or not. Then root locus is the same thing, graphical technique, and Nyquist method is the open loop transfer function frequency response. If you plot the Bloody diagrams, you can also tell about stability, okay, phase margin, gain margin. So it's a graphical technique. So I think we are coming through a number of techniques relevant to stability, okay, right. So it's time for us to look at what Lyapunov has figured out in terms of stability. So it is energy point of view. So in very fundamental way, it says this: if a plant accumulates energy, it is unstable. Okay, it will take a little time, but sooner or later it will become unstable if the system accumulates energy. So that is what it says mathematically, like dE over dt, rate of change of energy, right, greater than zero, right? Accumulated energy, this E is accumulated energy. So accumulated energy increases all the time, right? Then the system is unstable. On the other hand, if we see the rate of change of energy accumulation is less than zero, which means it is dissipating energy, and eventually motions are stabilized and it will reach an equilibrium point where state variables do not change anymore. Right? That is stability, stable scenario. Then this should be equal to zero, dE by dt equal to zero, then marginally stable, which means the accumulated energy, right, neither increases nor it is decreasing. Okay, it keeps the same energy at all times. It's marginally stable. Now it is to put this concept into mathematical framework. Okay, so let's start with the equation for a plant. So any time varying nonlinear system can be represented using this equation. Maybe you haven't seen this before, right? What you have seen is x dot equals ax plus bu. Remember, that is linear state space model, right? So x dot equals ax plus bu. But anything out of this linear framework, there's no particular way of writing, right? There are so many different types of equations, right? And they are all different nonlinear systems. So therefore, when we write down nonlinear plant mathematically, this is what we do. It's a function of state and time. So that you can have any combination of state variables, time, dependency, everything. Okay. So system is still state driven system. There are states. Okay. But you cannot have very elegant connection, right? Which is similar to the state space model, linear state space model, rather, that we discussed earlier. So this is the best we can do. We just symbolically write it to say that we don't know what it exactly is, right? It has to represent all of the systems available out there, nonlinear plans. So we just write a function of state and t. And also the output of the plant is combination of state variables, maybe one, maybe two, maybe all of them, right? So therefore, we put this C matrix as the output matrix to select and pick up the respective state variables as the output states. Now, we say a state is an equilibrium state, XE. We give a little subscript E to X to represent the equilibrium state. Okay. So if a plant moves to a certain distance with a certain velocity, certain acceleration, let's say 1 meter away from here with zero velocity and zero acceleration, is the stable point. You can have it like that. No, you have a vehicle which moves 1 kilometer, right? And at that point, it stops. It's not moving anymore. So you can say that it is 1 kilometer 0, something like that, right? So at that point, this function, right, f of x and t at that point is equal to 0. That is what we say. So all of the state variables will have to come to 0. The rate of change is 0, actually. Okay, rate of change is equal to 0. X dot comes to 0. So when x dot comes to 0, state variables do not change anymore, right? For all t. For linear time invariant systems, right? You can write it like that: dx by dt equals f of x and t is ax. If it is linear, okay. So we started off with the nonlinear plant. If it is a linear system, of course, you can write it this way. And this is what we have done earlier. X dot equals ax plus bu. So bu part we don't take here because stability does not depend on the control signal. If the system is stable, right, you can see it within this part. Okay, because it's a property of the system. So, and it further says that there is one unique equilibrium state, XE, if A is non-singular. Right? Non-singular means it's invertible. And there can be infinitely many equilibrium states, XE, if A is singular. If A is singular, right, there can be many equilibrium states. So we'll not take it very serious at the moment. We'll proceed. We will see it maybe later. And the other thing we want to keep in mind is that the equilibrium state XE can be anywhere, right? As I said in the previous example, a vehicle moving and stopping at 1 kilometer away, right? If you put your zero at that point, right, you don't have to say 1 kilometer, okay? You deduct 1 kilometer from your distance variable and redefine your distance from that point onwards. Then at that point, velocity is zero, acceleration is zero, and position is also zero. All right. So then all of the variables are zero. So in controls, we often do this. We call it coordinate transformation. And with respect to that point, we check the perturbation, right? Deflection around. So so for equilibrium state XE, you can write down the function as 0 times t. So time goes on, but state doesn't change, 0 for all t. Okay, right. Now take a closer look at this diagram. This is very, very important diagram. What we have here is our state space x1 and x2, two states, right? But you can extend the ideas to higher dimension, 3, 4, 5, 6, or n state variables, right? This is very easy to visualize with with two state variables, x1, x2. So now this point is the equilibrium point, as we discussed just a while ago. It's 0, 0, 0, 0, right? All of the state variables are 0. And remember again, this is not absolute 0, this is relative 0, right? Your operating point may be, your machine is operating at a certain operating point. This 0, 0 means that operating point, okay? And you want to see the deflection around that point. Now, there are a number of curves here, right? Curve number 1, curve number 2, this one, and curve number 3, this one, and curve number 4, this one, right? This is how the state changes of a plant, right? So maybe they all start from here. If I deflect the system from the equilibrium state along maybe this direction, okay, any of these lines, say over here, number 1 is very easy to see. So I'm here. I deflect the system from here to here. System was operating at 0, 0, and I introduce this perturbation. Now the plant is over here. It has a non-zero x1 and non-zero x2, and it drives its own. It drives its own now, okay? And x1 changes, and x2 also changes. And you keep tracking what happens to the plant. It moves like that, and stay somewhere here around this point. It will not come back to 0, but it will not go farther away as well. Okay, it will hang around. So it is one scenario. Another scenario is that, okay, when you deflect it over here, right, to point 2, right, this is maybe another system, okay, another system. What happens is that it will go to a certain trajectory and then eventually come back to 0, 0. It will come back to 0, 0. So this is very much like stable equilibrium point, right? Remember the diagram that we saw earlier? This one. When you deflect it, it eventually comes back to the 0. It will swing back and forth, but eventually it will stop there. So in the phase plot, right, we can draw the curves like that. And there's another one. What is that? Number 3. You deflect it far away, right? You deflect it far away. Big deflection of the plant, right? And earlier it was a small deflection. Now it's a big deflection. But interestingly, it comes back over here, right? So it looks like the system is has only one equilibrium point. So wherever you are, you have to eventually come back to that equilibrium point. Then for some other systems, it will be like this. You deflect from 0 to over here, and it will go like that. It will not come back to 0, right? It will eventually go to somewhere else. So it's totally different. It is kind of unstable. Okay, so these are the possibilities for a plant to undergo state change once they are deflected from the equilibrium point. So to understand that, we need to figure out the distance from the equilibrium point, and we write it like that: the norm x minus xe, right? Present position, present state minus the equilibrium state, and you get the Euclidean norm of that one. For n number of variables, this is how you write it. Individual states x1, x2, x3, x4 like that get their respective difference from the equilibrium point corresponding variable, and then get the squares, add them together, get the square root. Okay. And also in this discussion, we define two areas, right, around the equilibrium point. One is the smaller area here with the radius delta around the equilibrium point, and we define another area around the equilibrium point with the radius epsilon, right? So delta and epsilon. Okay, so with that, the four curves can be described like that. Number one, an equilibrium state x is said to be stable in the sense of Lyapunov. Stable in the sense of Lyapunov if trajectory is starting within delta, that the smaller scale around area around the equilibrium point. Okay, so if you do if you introduce the perturbation in that area, small area, right, the state trajectory, right, it does not leave the epsilon region, right? There's a bigger space, slightly bigger than delta. The trajectory will contain within that space. So that is what is called the stable in the sense of Lyapunov. Okay. Then number two, an equilibrium state is said to be asymptotically stable if trajectory starting within delta, that is a small area, you deflect the equilibrium point, but you are still within delta. Okay. Converges to xe without leaving the epsilon region. So it will come back to equilibrium point without leaving the epsilon region. It goes to epsilon region, but it does not leave, it does not go beyond epsilon region. Right? So that is what is called asymptotic stability. So this case is preferable to stability in the sense of Lyapunov. So if you look at the stability wise, number two is better than number one. Okay. So the first one is it does not return to the equilibrium point. It will move around, right? But does not come back to zero. Whereas the second case, it comes back to zero. It returns to the equilibrium point. That is the difference. Number three, an equilibrium state is said to be asymptotically stable in the large, asymptotically stable in the large, if trajectory is starting from anywhere in the hyperspace. Hyperspace means high dimensional space. So in the diagram, you see only 2 dimensions, right? But if you have 3, 4, 5, 6, 7 like that, it's hyperdimension. cannot be visualized. Okay, but you can imagine what happens, right? All of the other variables will have the same characteristic as of x1 and x2. So if trajectories starting from anywhere in the hyperspace converge to the equilibrium state, xe, it doesn't matter where you start your journey from, right? Or the initial perturbation, no matter how large that perturbation is, the state will eventually come back to the equilibrium state. So this is the most preferable case, right? Only one equilibrium state in the entire state space. And where you start your journey from, you eventually come to the stable point. Number 4 is pretty easy to understand. It's an equilibrium state which is unstable because the trajectory is starting within delta. Even a small deflection, this will leave the epsilon region gradually. Okay, right. So the purpose of this discussion is that to get your concepts in place, right? When we say stability, what you really mean by that, okay? There are different types of stability uh, nature, right? So let's look at a realistic example, right? So the Lyapunov stability has a couple of methods. So we'll take the first method, which is indirect and intuitive method. Okay. So this is our system equation, x dot equals function of x and t. So you can have any plant, right? Doesn't have to be linear all the time, right? And there's no need of solving state space model like in previous case. You had to solve the state space model, okay, like the determinant of si minus a and so on, right? Very methodical. And this method is non-unique. It's not a unique method compared to the previous methods like Rutherford's, Nyquist, root lockers. The system is very methodical and unique. But here, it's just a concept, and you have to implement the concept in your own way. So therefore, sometimes people don't like it because you have to figure out it eventually. Okay, Lyapunov only tells the concept. Right. So let's look at this simple problem. Very common in controls is a mass spring system. Right, mass spring. There's no damper, I guess. Yeah, only the spring. And you deflect it from this point to some other point and then let go. After that, you don't provide any force or anything from outside. The system moves by its own. Okay. So you can draw the spring, and the force through the spring is F, and you draw your distance Y, right, to the wall. So the motion happens, and we describe it here like y dot and y double dot, position, velocity, acceleration. This is the resulting motion after you letting the mass go, right, under the force of the spring. There, even though we don't have a damper, we have friction on the ground, right? The mass is on the surface, and there's a friction, which is also a damping action. So it is Cy dot, a viscous damping. The opposing force is proportional to the speed. So if you select your direction of motion towards left side, okay, the spring force is to the right, and against the motion, you have the friction force, which is to the right, and that is Cy dot. So this is your free body diagram. You have two forces, force from the spring and the force due to the friction. and the motion is to your left, y dot, y double dot. Now, one way of analyzing the stability is to look at the stored energy. Okay, stored energy. So if you think of a little energy, right, very small energy that is stored in the mass, right, because of the spring and all, right, is actually the force of the spring times dy. So if you move this force, the object to your left, right, with a little distance dy, under the force or against the force of F, the work done is force times the distance. So force is F, distance is dy, and that is delta E or dE, right? This is the stored energy of the system. Now, because the motion is on the horizontal plane, right, there's no change in potential energy. It's only the kinetic energy that is being stored in the spring. So the total energy in the spring, right, is what you get if you integrate this one for a certain over a period of time, F times dy, to integrate, and this becomes ky dy. Okay, this F is actually ky. Now, once you integrate ky, this becomes y square and in front of half. So it is half k y square. Right? The spring energy is half k y square. Now, this energy is stored in the spring. What about the mass, which is moving? So it has a velocity y dot, right? The mass is moving with a velocity y dot. The total energy is half my dot square. Okay, both these guys have some energy stored, spring and the mass. So the total energy of the system is the addition of these two together, right? So if you add these two together, you get the total energy. E spring and E mass, which is the kinetic energy of the moving object. So spring energy is half ky square plus energy in the mass is half my dot square, which is moving at y dot. So you add them together, right? What you get is the total energy over here. That is the energy. What we need to figure out is that what happens to this energy, whether the energy is accumulating or decaying, right? If this total energy keeps on accumulating, system is unstable. But if this energy is gradually losing, system is stable. That's very simple. If you want to check the stability of a plant, what you need to do is to find out the equation for total energy and then try to get the rate of change of that. If the rate of change of accumulated energy is negative, system is stable. So you differentiate it. You have the energy and you differentiate it with respect to time. So this becomes ky y dot, and this becomes my dot y double dot. So when you simplify, you can say ky plus my double dot times y dot. You get an expression for the rate of change of energy. Rate of change of energy, right? But we don't know yet whether this is decreasing or increasing. Now, while this is happening, we'll have to look at the force balance of the plant, okay? Force balance of the plant. So you can write down the Newton's equation of motion for the object, which tells you that if there's any imbalance force, right? If there's any imbalance force, then there's an acceleration towards that direction. Okay. So if you look at the plant over here, you can see there's a force to the left, which is 0, and there are 2 forces to the right, and vehicle is moving, or the object is moving to your left. So this looks like this is decelerating, right? Because there's no force towards the direction of motion, but both the forces are against it. So system is decelerating. But whatever it is, it doesn't matter. You can figure out your distance, direction, say y dot y double dot y, irrespective of the forces applied. Doesn't matter. Okay. The only thing is you get a negative sign.
Excuse me, sir, you are muted.
Oh, I'm sorry. So you can select your direction of motion, positive direction, freely. In this particular case, we have set it to the left, is positive, right? And we have 2 forces to the right hand side, which is against the motion, ky and cy dot. So because the motion is to the left hand side, which is positive, we write the equation of motion in that direction, leftward. Okay, so let's assume a force F, and then minus these 2 forces is equal to m times y double dot. Okay, so that is this equation over here. F minus ky minus cy dot equals my double dot. Now, because there's no F, we can set F to 0. So when F is 0, what you have is my double dot on the left hand side is equal to minus ky plus cy dot. So we have a relationship between say mass, acceleration, velocity, and position, equation number 1. Now, in addition to that, we already have this equation. This is the rate of change of stored energy of the system. Now you can see that this one, ky plus my double dot, you can see it over here, right? You can get that expression over here. All what you need to do is bring this ky to the left hand side. So when you do that, on the left, what you have is ky plus my double dot. Exactly this expression, which is equal to minus cy dot, minus cy. So this is what we are going to do now, right? From equation 1, my double dot plus ky is equal to minus cy dot, and we put that on equation number 4, right? 4 is this one. Then we can write down that dE over dt, rate of change of energy, is equal to minus cy dot y dot, which is cy dot square. Now we can clearly see that anything to the square is positive, right? Except 0. So y dot can be positive or negative, but when you square it, it is always positive. And C is the viscous coefficient, which is positive, right? We don't have negative friction in the world. Friction is always positive. So this is positive. This quantity is also positive. And in front of that, there's a negative sign. So therefore, rate of change of energy, dE by dt, is negative here. That is a proof, right? So we have just shown that the accumulated energy or rate of change of energy in the plant, right, is negative. So therefore, the accumulated energy reduces and eventually it comes down to zero and system is therefore stable. Is that clear? Any questions, please? Any questions, anything that is not clear? Okay. So then please take down this one, right? This is, even though I have written it like assignment, it's not an assignment, it's a take-home exercise, right? Write it down. There's a plant, x dot equals function of x and t. It's a nonlinear plant in general. And you are given the state equations. x1 dot equals like this, x2 dot is like this. Okay? You have the system equations. Earlier, you had the entire system, right, visualized to you, and you went on ahead and you wrote down the equations, right? Here, the equations are given, right? Now, can you take these two state equations and figure out what's happening to the system, right? Whether the accumulated energy is increasing or decreasing, right? Check the stability of the nonlinear plant. Please do this as a homework and get some practice. I'll leave it on screen for a few minutes, a few seconds rather, for you to take it down. All right. Shall we move on? Okay. So now, if you followed clearly the first method, right, which is very intuitive, the way you formulate the energy and eventually to get to the point where you figure out the sign of the rate of change of energy, right? Maybe be different to your friend's approach. So that is why we said this method is not unique. Okay, it's not unique. You have to do it your own way and eventually prove that the rate of change of energy accumulated is negative. Okay. Lyapunov did not explain a particular method to prove that. Now, before heading on to the second method of Lyapunov, right, we need to figure out some of the mathematics involved. So, first thing is the scalar functions of state vector, right? Please learn that when we say state vector, it is x1, x2, x3, like a column vector, okay? All the states. Now you can use a state vector and combine it with other matrices or same state vector, right? And multiply these numbers or do whatever operation. Eventually, it becomes a scalar. So then we call it a scalar function. Like energy, for example, is a scalar function. Okay. When you say energy, there's no direction, right? For energy, it's a quantity only. Now, we calculate energy from the state variables, but state variables are vectors, right? So when you calculate the energy from state variables, what you are doing is you are using the vectors and eventually get it down to a scalar. So we write it down as Vx, V of x, right? X is bolded because it's a vector. V is capital, but it's a scalar. Now, we say this, a scalar function of state x, that is Vx, is positive definite, right? We call it positive definite if Vx is greater than 0, right? Vx is greater than 0 for all x within a certain hyperspace. Within a certain hyperspace, right? So maybe you can think of the hyperspace we dealt with earlier. There's an equilibrium point and around that space. So within that area, right, if the Vx is positive, right, positive, then we call it Vx as a positive definite. You can have 0 at 0 only. 0 means the equilibrium state. So there's a function, we call it energy. So at the equilibrium state, it is 0. At the equilibrium state, it is 0. But if you deflect it in any direction, it has a positive value, positive energy, right? So if you have a function like that, we call it positive definite. Positive definite. Definitely positive, that is the meaning, okay? And the scalar function of state Vx is negative definite if Vx is less than 0 for all x around that area. So the moment you deflect away from the equilibrium point, your function is negative. So you can think of this as a paraboloid, for example, right? You know parabola, right? It's like this. At 0, it is 0, and after that is negative. And you can have the parabola going upwards like that, then it is 0 and positive. Everywhere it is positive if you have a little deflection. So these energy functions are like paraboloids, right? Like looking up, opening upwards, right? So minimum energy is at 0, right? It can be 2-dimensional, 3-dimensional, n-dimensional space, but there's one minimum point. Wherever you start, the system eventually brings the state down to 0, which is the 0 energy state. Our system is stable. Okay. But this energy function, this energy landscape may not be a paraboloid all the time. It can be something else. So therefore, this stability is not guaranteed. Okay. It is stable in the large. If it has only one equilibrium point, in that case, this energy function is a paraboloid. Now, the examples for this energy function or scalar function, let's call it scalar function, are these, right? What about this one, V1x? You get the state variables x1 and x2 and do it like that, x1 square plus x2 square. So what is that? It's the square of the two state variables and the summation. Okay. So this is a scalar function because even though x1 and x2 combined together is a vector, now you have taken x1 square plus x2 square. It's a scalar. And in linear algebra, this energy function x1 square plus x2 square is written like this, right? This is the state variable transpose. And then in the middle, you have unit vector, unit matrix, and then the state vector x1, x2. So when you multiply this vector with this matrix and then the result with this vector, this is the result. x1 square plus x2 square. So this is a very, very common thing in controls, particularly in the optimal controls, where you have to get the squares of the state vectors, state variables rather, and add them together, because a square of a state variable is called the energy of that state. So if you have n number of states, you have to get all of the squares of the state variables to tell about the total energy of the plant. So therefore, you will see this very often appearing in control system publications, right? Optimal controls. What about this one? X1 plus X2 square. You add them together and then get the square, right? What about this one? X1 square plus X1, X2. What about this one? Minus X1 square minus X1 plus X2 square. Right? The different types of scalar functions. There can be many more. But the point here is that if you have this one, x1 square plus x2 square, this scalar function is positive definite, because it is definitely positive, and it is 0 only at 0, 0, isn't it? Now, if you put 0 and 0, the answer is 0. But if you put anything else, the answer is positive, because it's two squares, right? What about this one, x1 plus x2 whole thing square? This is certainly 0 at 0. When you have 0, 0, the result is 0. We know that. But there are other situations also where you get 0 value. So if x1 is the opposite of x2, for all these combinations, the result is 0. So therefore you can have multiple zeros, okay, for every state where x1 is the negative x2 and vice versa, right? The function is 0. So therefore we call it positive semi-definite. Positive semi-definite. Okay? It will never go negative, but there are so many zeros also. What about V3x, x1 square plus x1, x2? This is indefinite, which means this one is actually positive or 0, right? It's not going to be negative. But this one, x1, x2, when the two state variables have different signs, that part is negative. So therefore, the system can have positive values, 0 values, and negative values also. So it's indefinite. The last function, V4, minus x1 square minus x1 plus x2 whole thing square, is negative definite, because it's definitely negative. It's definitely negative, isn't it? Whatever values you find out, say for 0, 0, it's 0, but for anything else, right? For negative x1, this is positive, but with this negative sign, it's negative again. And for negative signs over here, when you add them together, it's still negative, but when you get the square, it becomes positive. But with this negative sign in front, it again becomes negative. So it's always negative or 0. So it's negative definite. Negative definite. So you can construct these scalar functions using the state vector. Now, we have a bit more elegant approach to Lyapunov method, where the first case is not very unique, very methodical rather, right? It was like intuitive. You have to figure it out your own way to prove or verify the sign of dE by dt. But in the second method of Lyapunov, right, we have slightly different approach. So it says like this: if a positive definite function Vx can be found such that dvx by dt is negative definite, this equilibrium state is asymptotically stable, right? So this is similar to what we discussed earlier, right? But the difference is that rather than directly going to the energy, right, and trying to solve it and show its negative rate of change, I mean, right? Here, you can have any um, uh, positive definite function. You don't have to stick to energy itself, but any form of energy function, Vx, any positive definite function, okay? Then you have to differentiate it, right? Once you differentiate it, you have to get a negative definite function. You start off with a positive definite function, and once you differentiate it, you get a negative definite. If the case, then we say the equilibrium state is asymptotically stable. Asymptotically stable, which means wherever you start your journey from, you eventually come back to 0, 0. The convergence to 0, 0 is guaranteed. That is one thing. The second thing is the most common energy function or the positive definite function is this one, x transpose px. X is the state vector, you get the transpose, it becomes like a row, and then you have p, right? P is a real symmetric and positive definite matrix, okay? The matrix are also have positive definite, negative definite, and so on, right? You have to find out the eigenvalues of the matrix, and if they are all positive, is a positive definite matrix. So the P here is a positive definite matrix, and you put it in the middle of x transpose and x, and this is a scalar function, right? That is the most common energy function that we use in not only Lyapunov, but all of the other optimal control derivations, right? This is very common. Quadratic form, the square form, right? Now, sometimes you might get confused with the positive definiteness, right? Of a function and of a matrix. So for a matrix, positive definiteness is, as I just explained, please do your homework, study yourself about how to calculate eigenvalues of a matrix. How to calculate eigenvalues of a matrix. It's up there on the internet. Once you calculate the eigenvalues of a matrix, if all the eigenvalues are positive, the matrix is positive definite, right? Now the P here has to be positive definite. Otherwise, you can't take this Vx as your energy function, because Lyapunov needs energy function. So for your Vx to be an energy function, this P has to be positive definite, right? You can't just put anything there, right? To find out the positive definiteness of a matrix, you can use what is called the Sylvester's criterion. If you want to find the eigenvalues of the matrix, that's also fine. Find out the eigenvalues, and then you know whether it is positive definite or not. The other one is Sylvester's criterion. So the Sylvester's criterion is like this. Suppose you have this square matrix, okay? By the way, for any state space model, right, the matrix P here, right, according to the matrix here, the expression here, x transpose times x, right? P needs to have n number of rows to multiply with x transpose, because when you transpose x, it becomes a row and it has n number of state variables, right? And P is like, if you look at the first column, it has to have enough number of rows to multiply with the state variables. It comes like that, okay? And also on the other hand, P is multiplied with X. So X is a vector of n variables, and this guy needs to have in every row same number of elements to multiply corresponding elements, right? So therefore, P needs to have n number of rows as well as n number of columns. So it's naturally a symmetric matrix, a diagonal matrix rather. So, sorry, it's a square matrix, right? It's a square matrix, not a symmetric or diagonal, right? It's a square matrix. So if you want to find out whether it is positive definite or not, this is what you do. You take the first element on the top right, top left rather, and it is positive, right? In this case. And then you take the first 2 by 2 partition of the matrix and you calculate the principal minor of that one, right? Principal minor are submatrix determinants starting with scalar P11, right? You calculate the determinant of this 2 by 2 square matrix 1, 0, 1.50, and the determinant, right? So determinant of the first one is of course 1. Determinant of the second, a smaller matrix here, is 0.5, which is also positive. And finally, you get to the entire matrix, this 3 by 3 matrix, and get the submatrix determinant, which is 2.5, which is also positive. So if all of your principal minors are positive, the matrix is positive definite. So did you get that point? For any square matrix, you can get the principal minors, which are the determinants of the submatrices like that. And if they all are positive, the matrix is positive definite. In MATLAB, it's very easy to do that. You first declare your matrix and you declare submatrix 1, 2, 3, right? You figure out the partition, the portion of the matrix, right? Growing from your left top corner to the right bottom corner, right? First you take 1, 1. Second, you take 1, 2, 1, 2. Third, you take the whole matrix, which is 1, 3, 1, 3. So after that, the principal minor 1 is the determinant of submatrix 1. Principal minor 2 is the determinant of submatrix 2. Principal minor 3 is the determinant of submatrix 3. Like that, you get the answers. You can verify whether the matrix P is positive definite or not. Then we start the derivation process. Right. This will take a little while. So why don't we take a little break over here? Let's take a little break. All right. Sorry about that. So we differentiate the scalar function with respect to time, right? And we have 3 terms. So here, and the middle term, which is with p dot, is 0 because rate of change of a constant matrix is 0. And then we substitute for x dot because x dot equals ax. We replace this x dot transpose with ax transpose, and also this x dot with x, like that. Okay. So we don't have any dots here now, right? Then what we have is, as you know, when you get the transpose of a product, right, two matrices, so to matrix and a vector and all that. And when you get the transpose into the individual members or the elements, you swap the two together, right? So therefore, the AT whole thing transpose is equal to X transpose times A transpose, like that. So then if you look at the pattern here, X transpose A transpose PX, and then over here, X transpose P AX, right? You will see the pattern. You can write this down in this format: X transpose with the first element and X is the last element. Take these two out of the expression and put it in the front and the end, and collect the other terms from first one and the second element term into the bracket. So it is A transpose P from the first element and PA from the second element. Right? This is a compact way of writing that expression of two terms. Now, we can't solve this any further, just leave it there, right? Now, what we need to show is that if V dot X is to be negative definite, that is the requirement. We want to show that V dot X is negative definite, all right? For that to happen, because this X transpose and X, these are state vectors, right? This term in the middle has to be negative definite. So therefore, now the target is little changed now. Now we are after A transpose P plus PA. A is the system matrix, P is the positive definite matrix that we propose. Okay, we propose. You can have any P right over here, right? Together with X, the state variables, it makes the scalar function Vx. You can propose it your way, but make sure it is a positive definite matrix, because otherwise Vx is not positive definite. That's the problem. Okay, you can have any positive definite matrix P. Now together with A, right, this whole expression has to be negative definite. You start with positive definite P and this whole thing has to be negative definite. Right. So how to do that? It is not very easy to do it that way. Therefore, we need to have a different strategy here. So what we do is we introduce another positive definite matrix like Q, and we combine these two together, A transpose P plus PA and Q together with the negative sign here. So if this is true, ATP plus PA, this whole thing is negative definite because Q is positive definite. Okay, like P is positive definite, Q is also positive definite. And with this negative sign, right, this expression on the left-hand side becomes negative definite. So that is the technique we often use to show that A transpose P plus PA is negative definite. Right. So this is somewhat easier way. Determine symmetric P, right, and check for positive definiteness. So this technique is easier because if we use symmetric P, that is another thing. P has to be positive definite, and we can emphasize that P is symmetric. That's also okay, right? Then it is a bit easier to show that this whole thing, right, is negative definite for a positive definite P. For a positive definite P. So we have just few steps, right? Few steps. First thing is you find out any Q here. We'll first figure out Q. Put any positive definite Q and find out the P matrix over here. Symmetric P matrix, right? Symmetric P matrix. So, and show that it is positive definite. Then you are done. Any questions about that? I'm not sure whether you understood the point here. Now, the number one requirement is that the expression on the left has to be negative definite. So that we put positive definite Q here on the right hand side with a negative sign. So if this is true, the left hand side expression is negative definite. So the system is stable. All right. But to do that, we have two unknowns. We only know A, we don't know P, we don't know Q. Right? So that you can have a strategy. The strategy here is that you put Q, right? A non-positive definite Q. And then solve the expression for symmetric P. Symmetric P. Okay, there can be many P's, but symmetric P, we'll assume symmetric P, and then go ahead and solve for the elements of P and show that it is positive definite. So positive definite P, positive definite Q, two sides are equal, done. Okay, so that's what we need to do. So now I want you to take a piece of paper and work this sum with me, right? Take a little piece of paper and a pen. Without doing this, you will not get the real skill developed, right? Even though you can understand the theory, remember the theory, but to get some experiential knowledge, you need to work this. The second method of Lyapunov, right? Determine the stability condition of x dot equals ax plus bu, where a equals 0, 1, minus 2, minus 3. So you're given the system. You need to find out the stability criteria. Check the stability of the plant. So what we do, we straight away use the expression A transpose P plus PA equals minus Q. This is the stability criterion, okay? If the system is stable, this should be true for positive or positive definite Q and positive definite P. Both are positive definite, okay? And because we know that we can set Q our own way, right? Let's put Q equals I2 identity matrix. And remember, identity matrix is positive definite, okay? Identity matrix. I2 positive definite. And let's solve for symmetric P, which is A, B, B, C. So symmetric means off diagonal elements are equal and you have the main diagonal different elements, right? So this is a symmetric matrix, and we want to find out identity matrix, right, with positive definite case. So identity matrix we select here is 1, 1, right? Positive elements, so that it's a positive definite matrix, okay? Not negative identity, but positive identity matrix, okay? But with this negative sign in front of that, it eventually becomes negative, right? So what's on the right-hand side is this. It's an identity matrix with a negative sign along the diagonal. On the left-hand side, you have A transpose P plus PA. So you have seen, you see here A transpose, right? A is given. Now this is A transpose times P, and this is P. A, C, and BB of diagonal elements are equal, and then P times A. All right. This is A transpose. This is A. So when you multiply these two, you get this matrix. When you multiply these two, you get this matrix. Right? Now you have three unknowns on the left-hand side, A, B, and C. All right? And also you can, this is a 4 by 4, this is 2 by 2 matrix on the left and on the right. So which means you have 4 elements, right? So you can write down 4 equations if you wish, right? 4 equations. This one equals this one equals this one, like that. Element 1, 1 is equal to element 1, 1 on the right-hand side. Element 1, 2 equals to element 1, 2 on the right-hand side. Like that, you can keep writing 4 elements maximum, 4 equations rather. But the fact here is that the matrix P is a symmetric matrix, right? You don't actually get independent 4 equations. And you don't need independent 4 equations because you have only 3 unknowns to solve, A, B, and C, right? So let's move on. When you add the two matrices on the left-hand side, these two, right? The result is this one, minus 4B is the first element of the matrix of the left-hand side, and 1, 2 element is A minus 3B minus 2C, and 2, 1 element is also A minus 3B minus 2C. They are equal. And the last element, 2, 2 element is 2B minus 2, 6C. Okay. So with A, B, C elements, you get that matrix on the left-hand side. On the right-hand side is minus 1, 0, 0, minus 1. So you can write down equations if you wish, right? Minus 4B, this one is equal to minus 1, and you can find out B is 0.25. And also 2B minus 6C is equal to minus 1, right? And now because you know B, you can calculate C as 0.25. So like that, you can calculate A, B, and C, right? And also remember, due to the symmetry of P, we have only n plus 1 times n over 2 equations, independent equations, right? Because other equation here is actually dependent equation, right? So n is 2 here. This is a 2 by 2 matrix. So 2 plus 1 is 3 times 2, 6 divided by 2 means 3. You have 3 equations. And these are the 3 equations in matrix form, right? In matrix form. If you look at this one, first equation, 4B minus 4B equals minus 1. You can write it like that. Minus 4B means there's no A here, there's no C here. So these elements are zeros. And this is the variable vector A, B, C. We have 3 variables, A, B, C. Out of the 3 variables or 3 unknowns, right, we have 3 equations. And this matrix in front generate the 3 equations out of A, B, C. Some equations don't have A. So therefore, these elements are zeros, right? Some equations don't have C. So therefore, these elements are also zeros. Like that, you construct this matrix, right? Which construct the equations using A, B, and C. And on the right-hand side, you have minus 1, 0, minus 1. Okay. the right-hand side of the three equations. Okay, so you can go this way, linear algebra way, or just algebra way to find out A, B, and C. And eventually it turns out that A equals 1.25, B equals 0.25. You have already calculated over here. C is equal to 0.25 as well. Okay. Now, if you look at this matrix P, all of the elements, all four elements are positive. So therefore, P matrix is positive definite. There you are. Now you have positive definite P matrix, positive definite Q matrix, right, to satisfy this condition. Right? When you satisfy this condition with positive P and positive Q, what you prove is that A transpose P plus PA is negative definite. It's negative, which means the rate of change of energy is negative of the plant, so therefore plant is stable. That's how you use the second method of Lyapunov, which is a little bit more mathematically elegant than the first method. Any questions, please? Now, if you really want to prove that the P matrix is positive, you can use, you could have used Sylvester's theorem. I explained, right? Calculate the first principal minor, that is the element on the left top corner, which is 1.25, which is positive. So that is cleared. And the second principal minor is actually entire element, entire matrix rather, right, and get the determinant of that, which is 0.25, which is positive. Both principal minors are positive, so therefore the matrix is positive, definite. So our conclusion is the system is asymptotically stable, which means the system has only one equilibrium point, and even if you deflect within the workspace, state space, it will eventually find its way to back to the equilibrium state. Now, if you want to know a hard proof, the proofs you are familiar with, do this one, Si minus A determinant is equal to 0. So Si minus A is the characteristic equation, remember, when you set it to 0, the determinant, you can find out the closed loop poles, right? When you do that with for given A, you get the closed loops at -1 and -2. So both are on the negative half plane. Okay, real negative poles. So the system is obviously stable. Any questions, please? Is everything clear?
Yes, it's clear.
Okay. So that's it for the Lyapunov